Okay. So this is the second topic that we will cover in this course, inshallah, which is the economic dispatch. As we discussed earlier, we have several planning, operational planning and operation problems. And one of them is the economic dispatch, which can be classified as operational planning. While the system is operating, you need to plan for 1 week. This is called short-term load forecasting, and based on this short-term load forecasting, you need to schedule the committed generators in what we call the economic dispatch problem. We need to minimize the operating cost. The objective here of this problem is to minimize the fuel cost, the generating cost. We need to minimize this cost in order to get, of course, benefit or revenue of the assets that we spend in a power system. So this is the economic dispatch. What we will cover during this topic in general, and this will not be covered in one class, but this is the agenda for the whole topic. Definition of economic dispatch, and also we will see the operating cost and generator cost curves of the generators, and these curves play a great role in judging which generators should share by how much. So formulation of the economic dispatch problem, we will formulate it as an optimization problem, and an optimization will give you a very short briefly we will cover the operation optimization. We have two types of optimization problems. The problem can be unconstrained, and there is no limitation, no constraints. Just you have, for example, y. If I say y equal to x squared, there we are. Okay, y, everything is
flipped around.
Set up, yes. Okay, so y equal to x squared. If I say minimize, if I ask you to minimize this, so what do you think the solution? The solution is how much x that gives you minimum y. This is simply the solution of the optimization problem. What is the value of x that gives you minimum value of y? Can you solve this?
Yes.
0.
X
0.
equal to 0, and the minimum y equal to 0. Of course, if x positive or negative, then you have a squared, so y is positive usually, so y could be take 1, 2, 3, and so on. The minimum value of y is 0. So this is unconstrained problem. If I add to this problem, I say in x should be from minus 3 to plus 3. So this is a constraint. This is a constraint now. So you have to look for the value of x, which within this bounds, and also at the same time you minimize y. So this is called constrained optimization problem. If we remove this constraint, so it becomes unconstrained optimization problem. طبعا the solution of the constraint is you expect it to be more difficult. لأنك أنت unconstrained, you search for whatever value of x but here you have to stick with you have to satisfy the constraints. Okay, so economic dispatch solution neglecting losses and the generator limits. These are some of the constraints that could be an economic dispatch problem. If you incorporate the losses and also if you incorporate the generator limits, and we will resolve the problem, but here we will add the generator limits as a constraint, and we neglect also losses here. يعني the first part is this neglecting losses, and this is easy part, and this is more complicated, and if we add losses also, this will be more and more complicated. And we will cover this constraints which we are generator limits. So this is the problem. You have committed generators here, A, B, C, and you have load, and we need to distribute the load, to dispatch the load among the committed generators in order to minimize the generating cost. What would be the share? And if the load is 90 megawatt, what do you think the share of generator A, B, and C?
Doctor?
There are many possibilities.
Doctor, I have questions.
Okay, raise your hand, please. And I didn't see any hand raised. So, okay, Salah, Abdullah.
Yes, Doctor. Does the distance affect which generator should be on and which one should be off? I mean the distance between the load and the generator.
طيب أنت, if you think about it, let me.
I would say it depends on the load, whether it's reactive or real power.
لا أنت يعني أنت بتتكلم عن distance now.
Yes.
Right?
Yes.
Whatever the nature of the load, leading, lagging, power factor, whatever the load is. Now you ask whether the distance between the load and generator affect the distribution. Anybody has an answer for this? Does it affect distance?
Yes, I think
Malik,
because of
Malik Ali.
Yes, I think it affects because it's as longer the distance, as more resistance we have.
Okay.
So it affects the load.
More resistance معناها more ايه؟
More load.
لا more losses.
More losses. Yes.
More losses transmission line. More losses in transmission line. يعني الcost will be higher لأنك أنت you need to generate if the load is 90, you need 90 megawatt for the load. So if we have here a big distance and you have here 10 megawatt here losses in this transmission line, so in this case you need to generate from here 100, assuming طبعا there is no here. So you need to generate 100 اللي هو 90 plus losses. Definitely the cost will be higher. Okay, so definitely the answer is yes. Distance affect the dispatch. Of course, we prefer if you have a generator here. This is a bus, and you have here another bus. You have here generator 1, and you have here the load. If you have a generation here, G2 is most preferred than G1 to supply the load. There is no losses here. It is the same substation. Okay, so there is no losses here. This is most preferred from the far generator. This is why, Shabab, this is why the concept of renewable energy is is a hot topic nowadays, or last 10 days and so on. And you can see also the plan of the kingdom to have like 40 gigawatt of PV, photovoltaic source, solar energy, and 16 gigawatt of wind, and 2.7 gigawatt of concentrated solar power, solar heat energy. And also we have what we call the microgrid. Microgrids, you have maybe PV and wind and CSB and some diesel generator next to the load, very near to the load, so they supply the load here economically with renewable energy. So in this case, you don't need much power from the transmission line. You can reduce the losses in transmission lines, and you can also save for the generator or generation of the electricity. So definitely distance will affect the dispatch. This is for sure, as we will see in a minute. Okay. So several generating units serving the load. Definitely, we don't have only one generator to serve the load. Load is distributed over the wide geographical area. And you have different, of course, generation plants to be committed. What share of the load should each generating unit produce? This is the solution of the economic dispatch. What if the limits of the generator units are considered? Okay, so here we can say, no, this is just the unconstrained problem. And here we add the generator, the limits of the generator limits of the generator outputs into consideration. And what if the limits of network are considered? The limits of the network is just the losses, and also the line flows. Okay. So you need also to observe.
Sir?
Yes, please.
What do you mean by line flow?
If you have here one generator, and this is another generator, and you have here another generator. Okay, so maybe this is also connected here. You have here some loads, load 1, and you have here load 2, and so on. You need to distribute the summation of these loads among the generators. Now, if you have this line can carry maximum 100 megawatt, maximum, and this line can carry 50 megawatt only, maximum limit of line flow here is 50, and here you have مثلا 70 megawatt. Okay, so these are the maximum line flows. These are the line capacity, let us say. Now if you solve the economic dispatch problem and you found this generator, for example, produce, let us say this one produce 170 مثلا، خلينا نقول 170 megawatt. So this 170 megawatt, طبعا we have here a load. The load could take some of the generated power, and when you have distribute the remaining power among these two lines, okay, so this line you find the line flow is 60 megawatt.
Overload.
So the line here is overloaded.
Mm.
So you have to observe also this is what we mean by the network constraints, losses and the line flows. Okay, so this is will lead us to the problem that we discussed earlier, which is called security, power system security. So if you do dispatch as such, would be the system secure or not? Is there any violation? If there is violation, as you can see here, 60 is greater than 50 megawatt, so this line is overloaded. In this case, we have to revisit the economic dispatch problem and resolve it considering this violation here.
Clear, Doctor.
Okay. طيب, since the load is variable and there must be enough generation to meet the load, as we mentioned, in electricity is a fresh commodity. And you generate and consume. No storage, unless of course you have energy storage like batteries or supercapacitor or whatever. But generally, حتى even the energy storage systems is still, this is a bottleneck in power systems, اللي هو energy storage. You cannot store energy in high capacity so far. This is.
Doctor, what's the maximum for the storage? Maybe.
لا, هو في some trials, some implementation for, you can say, you may have مثلا 200 megawatt storage. 400 megawatt storage, that's all maximum installation in real life. So still طبعا انت you are talking about مثلا Saudi Arabia network, you have about 70 gigawatt. So this or even this, if it is 400 megawatt, so this may be over or 400 over 70. The ratio is very, very small.
Yes.
Very, very small ratio compared to the generation. Still, energy storage is a bottleneck in power systems. فطبعا as I mentioned, electricity is a fresh commodity. You have to generate and consume directly. So Abbas, Fuhed, if you have a question, Abbas.
Yes, I have a question.
Please.
Yes, why cannot we store more power? Because it's only a matter of capacitor. We built a huge capacitor, so we can store it. Is there any constraints that prevent us from storing power?
وأولا الستورج بيبقى في باتري. اوكي، مش كاباسيتور. انت الباتريز ستيل، التكنولوجي بتاع الباتري از ستيل ليميتد.
Yes.
they have lead acid battery اللي هي موجودة عندك في السيارة ولا whatever. وبعدين they have like lithium ion battery زي اللي موجودة عندك في الموبايل. دي تكنولوجي كانت very break through for battery. طبعا في اعلى منها وحاجات زي كده، او big size from مش بس الباتري بتاع الموبايل، لا في برضه lithium ion same concept, but you can have like مثلا in electric car you have مثلا battery of 24 kilowatt hour battery. Okay, still الباتري as I mentioned, and we can just store 200 or maximum 400 in some applications in Australia and in US. They have some real life installations of battery, but within this range, which is very, 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 very low compared to the generation capacity that you have. فالباتري is very expensive. يعني الانرجي ستورج systems generally they have pros and cons for each one. So if you need to go مثلا for example there is another energy storage system called superconducting. Superconducting energy storage system, where you have like a reactor which store the energy as magnetic field, but this coil is superconducting coil. Yani you have to cool this conductor to very low temperature, like minus 200 degrees centigrade. So this is also very expensive. In this case, for this type of energy storage, you can store around 100 megawatt. Okay. طبعا انما الباتري is limited. يعني الباتري is limited capacity. يعني فيعني في there are some technological challenges in the energy storage systems. Okay, so
still, Doctor, I mean, why can't we use capacitor? What's the
الكاباسيتور
سوبر كاباستور.
طيب خلينا نقول انت ادام قلت سوبر كاباسيتور، خلينا نشوف برضو السوبر كاباسيتور. يعني السوبر كاباسيتور you have سوبر، خلينا نقول اس سي. الاس سي could be مثلا thousands of farads. يعني you may have مثلا 5000 فراد كاباسيتور. طبعا ده ما كانش الواحد يحلم بيها قبل كده. يعني يبقى الكاباسيتور كنا دايما نقول مايكرو فراد and so on. انما دلوقتي بقى ممكن you can have a capacitor, very small capacitor. It is not like يعني you can have like a cup مثلا size. You could have 5000 farad capacitor. Okay, now this capacitor or this super capacitor is high power density. And low energy density. This is opposite to the battery. Unlike the battery has high energy density but low power density. ايه معنى الكلام ده؟ انه الكاباسيتور could give you high power but in very short time. يعني ممكن تخزن فيه طاقة كبيرة، مثلا say 1 megawatt. It will give you 1 megawatt but only for 1 second, for 2 seconds. Okay. انما الباتري could give you low power, few kilowatt, but for long time. You can have 10 hours. The battery could supply this low power for 10 hours. So the energy density is high in terms of يعني every يعني still there are, as I mentioned, يعني challenges for the energy storage system. طبعا the research is hot in this area in order to improve the capacity and of the energy storage, and also to manage this, or you can have also hybrid system. If you can combine super capacitor with battery, so you can combine these features together and avoid the drawbacks. يعني there are a lot of يعني issues here in energy storage. We don't want to يعني go deeply in this in order to يعني move forward in this. But if you want to discuss more at the end of the class, you can stay. We can discuss more. Okay, Abbas.
يعطيك العافية دكتور.
Okay. طيب, optimally determining which generators to use can be a complicated task due to many different constraints. For generators with low or no cost fuel, if you have wind generator, if you have solar PV, this is almost no cost. Almost, okay? There is no fuel here. You need also to utilize them efficiently. And you need to extract the maximum power from the wind, maximum power from the solar PV. So you have to take this into consideration when you dispatch. But unfortunately, this type of renewable energy, we call them undispatchable. Undispatchable sources. And you cannot rely 100% on those sources. In no time, the wind power could reach to zero. Okay, and if you have wind with 5 meters per second or 10 meters per second, and you generate 100 megawatt, maybe in 1 or 2 minutes, the wind stopped, and then you have the output power very, very low. So the ramp up and the ramp down here is very sharp for wind and also for solar PV. If you have cloudy sky, and if you have cloud in the sky and you have shading on the panels, these panels, the output of these panels abruptly go down. You have to be careful with the renewable energy sources. One of the solutions to this issue is energy storage. If you have energy storage combined or integrated with wind and PV, this will, this will make the problem not as hard as without energy storage. Okay. So for others like hydro, there are they may be limited energy for the year. And in hydro, you have also to be careful, or you have to look at the energy for the year. You have a reservoir, and the reservoir has a capacity, and you expect, for example, 10 million cubic meter rain, and you need to drain this 100 million cubic meter. And you have to drain this whatever. This is the whether you need the power or you don't need the power. You have to you have to drain this amount of water. And also maybe you have shortage on water, but you have also to drain some water for irrigation and farming and these activities. Some fossil has shut down and start up times of many hours. Also in dispatch, you have to look at this issue. Some of the generators, it takes 3 hours to shut down, after shutdown to start up again, and when you start it up, it may take 3 hours to be in full on full utilization. An economic dispatch looks at the best way to instantaneously dispatch the demand among the committed generators, as you discussed earlier. We have traditionally, we have 3 types of loads. We have what we call the base load, mid load, and the peak load, and each load you have to schedule some units to cover this. For example, if this is the daily curve, this is 24 hours of the day here, 24 hours, and this is the power needed. This is the your forecast. You forecast the load as like 5,000 here, about 5,500, and then for this hour you and so on, you forecast the maximum power here at 4 p.m. and so on. So this is the daily curve. This is the load curve. So as you can see here, and you have some minimum load which is constant for 24 hours. So this is called the base load. And you have some sustain for long time. This is called the intermediate load. And this is for few hours. This is called the peak load. So if you have 10 generators and you know the generator characteristics, you have like hydro, and you have some nuclear power plants, you have some thermal power plants, and also you have some gas power plants. In this case, you distribute, you say no base load, for example, we will cover the base load for hydro if we have, and the nuclear. Okay, so this will cover some of the thermal generator also. Okay, so this will cover the base load. If we need more load, then we will we will commit some of the also thermal gas turbine. For peak load, we need some generation plants which can be committed or put in the on operation very fast, and you can shut down after maybe 1 hour or 2 hours needed only, and you shut it down. So this could be for gas power plants and the peak load. So wind and solar PV can be quite variable, as we discussed. Usually they are operated at maximum available power you need to extract from them. And no, there is no fuel here, there is no cost, almost zero cost. طبعا almost zero cost running cost, we mean running cost. انما طبعا installation cost still you have some So this is example of the wind output for a month by hour and a day. You have here 24 hours for day 1, day 2, day 26, day 9, day and so on. So you can see here some days very low power you can have. Some days you can have high power like this. This one you have high power all the day, but here the power of the wind is little bit decreased. And look at this curve. مثلا, this one start very nice at the beginning, and then within 1 hour you can see how much the change from 600 megawatt output to almost 100 megawatt. So this is very very problematic issue for the power system operator. He has to respond to this fast ramp down of wind. And also ramp up also is also another problematic issue. Either you decrease or decrease, we have to take into consideration such issues in dispatch. Okay. So the two main types of generating units are thermal and hydro, with wind rapidly growing. For hydro, the fuel water is free, but there may be many constraints on operation of hydro. Fixed amounts of water available. You have to look at the reservoir levels, must be managed and coordinated. Downstream flow rate for fish and navigation. Also, you need to have some flow for fish and irrigation and farming and so on. Hydro optimization is typically longer term, many months or years, لأنك أنت you expect how much rain that you will get this year and so on. So this is long term planning, let us say. few months and years. We will concentrate on thermal units. طبعا in Kingdom we have only thermal units and gas units. For this is this is the case here. So generally this is the schematic diagram of the generation plants. You have here a boiler. This is for the thermal power plant. You have boiler, and this boiler needs fuel to be burned in order to generate steam, and this steam will go to turbine. You have here steam, and this turbine you have here mechanical input, be mechanical, and here is the electrical power output from the generator. And this is turbine, could be a 2-stage or 3-stage turbine, high pressure turbine, medium pressure turbine, low pressure turbine. You can have some reheating also in order to increase the efficiency and so on. But this is generally the schematic diagram of the generation plants. You have input here through the fuel. You have heat energy input, heat energy, and you have here electric energy output of the plant. To optimize generation costs, we need to develop cost relationships between the net power output and the operating cost. We need to find, okay, if we have 10 megawatt output, how much the cost? If we have 20 megawatt output, how much the cost would be? 100 megawatt from the generation plants, how much the cost? Can we have the function here between the cost and the output power? Yes, we can have a cost as a function of power output, or be generated. This function could be linear, could be non-linear or quadratic. And you may have non-linear, you may have linear. And we can say in the cost equal to 10 plus مثلا 0.5 B, مثلا BG. So if this is the cost, if B equal to 10 megawatt, this will give us cost equal to 10, 5, 15, and so on. Okay, so this very important curve or very important relationships that we need to solve the economic dispatch problem. How much the operating cost as a function of the output power of the generator. Okay, we will see these such curves in few minutes. Operating cost and generator cost curves. Factors influencing the minimum cost. If you have any question, please ask. Factors influencing the minimum cost of power generation: operating efficiency of the prime mover and generator. This is a big issue or important factor that affects the dispatch problem. The efficiency of the generators, the efficiency of the turbine also. You have to take this into consideration, and this will affect the cost definitely. If you have overall efficiency equal to 30%, معناها انه you pay for 100 and you get out only 30 megawatt. انما if you have better efficiency 50%, then this 50% means you can get from the same input you can get 50 megawatt. So operating efficiency is very important. طبعا efficiency is the efficiency of the overall plant. أنا بقول 50%. يمكن حد يتساءل الجنريتور الافشنسي بتاعته very high. الجنريتور could be 99% or 98%. انما طبعا الcost in general, it's not only the generator but also the turbine and boiler. The overall efficiency of the plant could be very low, by the way, and thermal power plants could be 30%. يعني the overall efficiency could be 30% or 40% for the thermal power plants due to have this turbine and boiler very low efficiency. Maybe in gas power plants, the efficiency could reach to 60. If you have combined cycle, this is the open cycle. If you have closed cycle or combined cycle, you may have 85% efficiency for the combined cycle. So the efficiency plays a great role in dispatch. The fuel costs also. يعني these power plants use مثلا sea water, okay, for generating the steam. The fuel could be coal or could be crude oil. For thermal power plants, for gas you need gas, of course. This is the fuel. Gas is the fuel. So definitely gas is more expensive than the coal. Gas is more expensive than the crude oil. Definitely we need to have this gas at the peak load generate some electricity at few hours a day. So the fuel cost also will affect the dispatch. Transmission losses with distance, as we discussed earlier. Also transmission losses will affect the dispatch. The most efficient generator in the system doesn't guarantee minimum cost. Muhammad Hassan, do you need a question? Do you have a question?
Yes. What do you mean combined
combined cycle? Our closed cycle, you can have this is the turbine. You have here gas. Okay. You have gas, and definitely this gas will, we will have some mechanical power here, conversion at the end. But some of the gases are going to the air, like this gas, the exhaust here. This is exhaust gas. This is the exhaust gas. Okay, so you keep it going to the air without any usage of this. But for the combined cycle, let us utilize this heat gas, which is output from the turbine here, in order to heat up some water, and we can have another generator here, another turbine here, and this gas will considered as a fuel for the steam here to generate the steam and to generate the electricity, another part of electricity here. So you have two outputs of electricity, right? So you have here, or you can use this to generate steam, and in your industrial plant you may need steam. In some of the processes you may need steam, but you can generate the steam from here. So the steam here is output also will be considered plus this output. So you increase the efficiency of the turbine.
Is this cogeneration?
Yeah, this is called cogeneration. Yes, yeah. Cogeneration means when you have electricity and steam. You cogenerate electricity and steam. Here you use the steam directly, but sometimes you can use the steam to generate also electricity, right? You can do this. Well, cogeneration is you can have electricity and steam at the same time. Okay, so this of course will increase the efficiency of the gas turbine, compared to just keep the hot gases goes to the air without any benefit of them. So the most efficient generator doesn't guarantee minimum cost, لأنه ممكن يكون ال most efficient generator may be located in the area with where the high fuel is very high, the fuel cost is very high, or could be very far from the load center. يعني you have a big or long distance between that generator and the load center. So the problem is to determine the generation at different plants to minimize the total operating cost. اللي احنا عاوزين نقوله ان solution of the economic dispatch is not an easy task. It is very complicated problem. You need to optimize it. And it is not just intuitively you can say, no, let us take this generator or take this generator. You have to look at all these issues that we discussed here. So the cost curves and that we need to solve the economic dispatch problem can be classified as four curves here. Input-output curve, which is a relation between mega British thermal unit per hour versus megawatt. Megawatt اللي هي الاوتبوت electric power, and this is the British thermal unit. So this is the input of the generation plant. You have the fuel, and each fuel has a certain British thermal unit. So the size or the amount of fuel that you use gives you the amount of British thermal unit input to the generation plant. Fuel cost curve. And instead of expressing the fuel here by British thermal unit, we can have the fuel here in terms of cost. You need, مثلا, for example, 1 barrel of crude oil equal to, or يعني, the cost is $20, so you can multiply this amount of the fuel by the cost. So you can have the fuel cost curve. This is dollar per hour instead of heat energy here. Dollar per hour versus output power اللي هي megawatt. The heat rate, again you take the heat energy over the megawatt hour versus megawatt. Incremental cost. The incremental cost is dollar, and you divide here by the, you can say, let us normalize over the megawatt hour. Dollar instead of dollar hour per hour, dollar per megawatt hour. MBTU per hour, MBTU per megawatt hour. So these two curves is just scaling from this previous. And this one also is a scaling of this. You just multiply this by the dollar per British thermal unit, so you can get this. So all these curves are, you can generate from one to another by just scaling or multiplying or dividing by a certain value. Just to for your reference, the British thermal unit is 1054 joule. It is an energy unit. So 1 mega is طبعا 10 to the power 6. 1 mega equal to, if you have this, joule is equal to watt second. And if you want to put it in terms of hour, so you divide by, طبعا you have here mega, so you divide 10 to the power 6 over an hour equal to 60 minutes, and you have here also 60 seconds, so you divide by 3600, so you can get this number. And of course, if you need 1 megawatt hour, then it is 1 over this value, which gives you 3.41. يعني this is just for transformation. يعني you don't need to have this. If you have this one, you can generate those. The input-output curve, as we mentioned, it is British thermal unit per hour versus megawatt. So you can have this input power and this is the output power. So here, مثلا, for example, to generate 200 megawatt, you need this amount of energy to be to burn the fuel in order to have such amount of output power that we need. طبعا this curve is linear, but this is not always the case. You can have you can have parabola. This could be. You can have piecewise or piecewise curve. You can have curve like this one you have here, and then you have another one here, and then you have another one here. So this curve could be discontinuous. لأنك أنت here you switch the type of fuel. يعني maybe for low load we will use مثلا a certain type of fuel. But when the load increases, we have to switch to another type of fuel. So we have another curve here. And if we have another type of fuel at a certain amount, 100 megawatt, then the cost will increase dramatically. So we have to change the fuel. If we switch the fuel type, then we have some discontinuous function as such. This is also could be in real life. You could have this if you have fuel switching. Ryan Adib?
Yes, Doctor. How to differentiate the rare input-output?
How to differentiate?
The heat rate curve. Then this
here. The heat rate, if you look at the heat rate is MBTU over megawatt hour. And you divide here by the power, megawatt. Here you have hour. Okay? So this is the input output. Did you get the point, Ryan?
Yes.
Units is different here. This is mega British thermal unit over hour. So this is the input output curve. So from this curve, as I mentioned, you can with 100, this is the amount needed as input. The fuel cost curve وطبعا the same as before, same as this one, but you multiply this by the cost of the British thermal unit. Assume that in the British thermal unit cost you, for example, $600 to generate mega British thermal unit. So this will be scaled to 600. Okay, is it clear? It is just rescaling here of this fuel cost dollar per hour versus the generator output. So for 200 megawatt, you may need about $4,000 per hour. This is the running cost or fuel cost here to generate 200 megawatt. So you need that amount of dollar here. Okay, this is the heat rate, mega British thermal unit over megawatt hour. So this is the curve as you can see here. طبعا انت you divide per hour, that means you have some non-linearity here. This is the curve. And this point, لأنها minimum point, here this best for most efficient units are around 9 here. يعني you have around 9. لا طبعا it's not 9, but you have it here 10 point something. Yeah. So this is the if you generate only from the power from the generating unit about 180 megawatt, this will give you the minimum cost here. Incremental plots incremental dollar per megawatt hour as a function of megawatt, dollar per megawatt hour, or versus the megawatt here in x-axis. طبعا of course you can get the derivative as we will explain more details here in a few minutes. Mathematical formulation of costs. Generator cost curves are usually not smooth. As we mentioned, you may have linear, you may have non-linear, you may have discontinuous also if you have some fuel switching. And not only discontinuous, you may have a curve, a cost curve like this one. This is the cost, dollar per hour versus the power. You can have, as I mentioned, you can have linear, you can have quadratic, you can have discontinuous. If you have, even if you have continuous like parabolic or quadratic function, you may have such curve. Here, this reflects the valve opening action. Then if you need to increase the power, how to increase the power output? Here the power is increasing. How to increase the power output? You increase. How to increase the output power? So you increase the
Increase the steam.
You increase the steam going to the turbine. And you have here turbine, and this is the generator, and this is the output power. You have here valve, and this is the boiler. So you have here this valve controls the steam that goes to the turbine, which will affect definitely the mechanical power input to the generator. If you need more power here, you have to open this valve more to increase the opening of this valve, to allow more steam, to allow more power, to allow more power here. So this is what we call the valve opening. When you open this valve, the opening of the valve is not smooth. This is a mechanical, device, and the mechanical device may take some time constant is long, and this could happen here for the cost curve. You have like a sine. This could be represented as a sine wave, as we will, could be non-linearity embedded here in the curve. This is could reflect the valve opening here. Type. Okay, so it's not necessarily to have a smooth curve. You can have, as I mentioned, linear, quadratic, discontinuous, and so on. Are usually be adequate to approximated using piecewise smooth functions. Usually طبعا لانه الاناليسيس with such non-linearity, or if we have a switching, and this will be complicated. فاحنا we will confine our analysis here for just if we have linear, cost, or quadratic at most. Okay, and the smooth curves here. Two representations predominate, quadratic or cubic function. يعني the cost is function of the power, quadratic or cubic function. يعني you can say A plus B times the B generated plus C times the B generated square. So this is a cost. This is a cost function if it is quadratic. If it is cubic, you add here another term with the big G cube. Okay. Or you have piecewise linear curve or linear functions here. Generally, the quadratic representation is assumed. You have here constant beta times bg and gamma times bg square. So this is a quadratic function. الانكريمنتال cost أو الانكريمنتال cost, you can differentiate this function to get the incremental cost. The incremental cost is very important يعني in terms of the physical meaning of the incremental cost is very important, and this also plays an important role for in dispatch problem. We will discuss now the physical meaning of the incremental cost. You have the cost curve. If you differentiate the cost curve, you get the incremental cost. So you have here alpha, beta, and gamma, b square, and so on. If you differentiate with respect to bg, definitely this will diminish, and you have beta plus 2 gamma multiplied by bg. So you can say here انه طبعا البيتا والجاما are constants. You know them. 5 مثلا plus 2 times 0.2 في البي جي. So if you need to generate one more megawatt, so how much cost you will pay? So you can substitute here عن البي جي from 11 to 12 مثلا megawatt, so you can see how much cost to generate 1 megawatt at this level of loading of the generator. The physical meaning of incremental cost is very important, as we will see in more details later on. So for a two generator system, let us assume a very simple example. Muhammad Hassan, do you have a question?
Yes, what would be represent?
What would be what?
Represent.
The physical meaning of the incremental cost represent how much cost, how much dollar you will pay in order to generate only 1 megawatt, additional 1 megawatt. Okay? So it gives you, for example, if you go back here, if this is 5 plus 2 times 0.2, 2 gamma times BG. Okay? If the generator generates at this instant BG equal to 10 megawatt. If you substitute here on the BG equal to 10 megawatt, so the incremental cost equal to 5 plus you have here 10 times 0.2, 2 times 2, 4 plus 5 يبقى 9. So you will pay $9 in order to get 1 megawatt more, in order to move from 10 megawatt to 11 megawatt. So this is how much the cost you will pay. Okay? Is it clear? Yeah.
Yes.
Right. Okay. Now we have a very short quiz. We need to take it. Let us see.
Is it through the blackboard?
Yes, it is through the blackboard. ما خلاص ما انتوا قلتوا through the blackboard is better okay. We will take it in a few minutes. So C1 cost equal to this quadratic function. The cost of the generator 2 equal to this quadratic function, dollar per hour. So the incremental cost for the BG1 for the first generation plant is you can take the derivative, so it becomes 20 plus 0.02 times BG1, and the incremental cost for BG2 equal to such 15 plus derivative here, it is 0.06 times BG1. Okay. If BG1 equal to 250 megawatt and BG2 equal to 150 megawatt, of course you can calculate the cost. You can generate substitute here and BG1 equal to 250 and the 250 square, the other one 150 and the 150 square. You can calculate the cost. And also here you can calculate the incremental cost, 250 and 150. It's very simple. You can just substitute. So at this level of loading of the generator number 1, the cost equal to 6,625, okay, dollar per hour. For 150 megawatt for the generator 2, the cost is 6,125 dollar per hour. So the incremental cost for this one is 25. The incremental cost for this one is 24. So if you want to move from 250 to 251, you will pay $25 in addition, and for this one, you will pay $24 only. Okay. So simply the problem formulation can be highlighted as such: the economic dispatch, the objective, and the constraints. This is the optimization problem in general. Optimization problem, you have to define objective function. What is your objective? Is to minimize the cost for all generators. If you have 3 generators, each generator has a certain cost function. You add all the costs here, and you need to minimize this cost, such that, or subject to, these are the constraints. The summation of the generation must cover the load plus losses, right? Is it clear?
Yes. Yes.
Okay. So these are the cost function and the constraints, as I mentioned. The summation of the generations must cover the demand and the losses. And also another constraints is each generator has limits, the minimum power and the maximum power. So each generation plants has a bounds of the minimum power can be generated and the maximum power can be generated. So when you solve the dispatch problem, solving the dispatch problem is getting how much BG1, how much BG2, how much BGN. This is the solution. And you have to make sure in this BG1 lies in between BG1 minimum and BG1 maximum. Otherwise, your solution is not feasible solution. We cannot, consider it. Okay. So, and I will give you the quiz now. The quiz is just for 4 minutes. That's all. And okay, so you can. I will make it available now. It's very simple quiz. بلاك بورد خلاص احنا قلبنا على البلاك بورد، يعني based on your recommendation فاحنا قلبنا على البلاك بورد. اوكي. والله today is what? 30?
عطنا كذا 3 دقائق زيادة دقائق. زيد
Yes,
دقائق
yes.
يا دكتور.
انت لسه شفت الكويز عامل ازاي عشان تطلب دقايق زياده؟ الكويز فيري سمبل. خلاص ماشي، نديك 5 minutes. خلينا نقول مش عارف. طيب let us stop sharing at the time being. Just go here. Do you have any question? If you have any question, please, we can discuss it until we have this ready. Maybe I stayed for a long time inactive. This is why it is needed to be reactivated again. So you have the quiz now available?
Yes.
Yes, doctor.
So go ahead. You have 5 minutes. And I think after 5 minutes, the class is over. So in this case, you just submit and leave. If you have any questions, stay after submitting the quiz.